Last year, we introduced the Universal EV platform and production system at Louisville Assembly Plant. But this journey started years ago with a single ambitious goal: build great electric vehicles that are not just fun to drive, but genuinely compete on price with the best, including gas vehicles. An electric vehicle's battery can account for about 40% of its total expense, which is a major barrier to affordability. Thousands of people globally are working on reducing the cost of batteries, from the raw materials all the way to the ways that they're manufactured, to make them more affordable. But it's important to work in parallel on reducing the size of the battery in an electric vehicle. To address this, we needed to start completely from scratch, rethinking how we approach design, engineering, and manufacturing of a vehicle together as a team. Why such a radical shift? Electric vehicles are basically a massive physics challenge. We know that many customers expect more than 300 miles of range. And the solution up until now has been to install bigger, more expensive batteries. This increases the weight, and that requires even more energy to move around. And traditional vehicle designs tend to be aerodynamically inefficient, putting even more tax on the battery. We knew we could do better by focusing on one thing above all: efficiency. And we did this by arming every engineer working on the project with what we call bounties. Bounties are numerical metrics we assign to key factors like vehicle mass and aerodynamic drag, factors that directly translate to efficiency and therefore the range and the cost of the battery. In a low-cost vehicle, it can feel counterintuitive to increase the cost of a part just to decrease its weight. But if we can give that weight reduction a value in terms of the battery cost, then we can decide if making the part lighter and more expensive actually saves us more money than adding additional battery. Bounties guide our engineers to make these tough trade-offs. The aim is to reduce overall energy consumption of the vehicle as a system, not simply an optimization of a single part. It starts with our all-new midsize electric truck. Let me pass it over to Salim to talk about aerodynamics and parasitic friction.
Aerodynamics is a crucial part of an electric vehicle's performance because every bit of inefficiency caused by drag robs you of range. At higher speeds, drag becomes even more significant. If you go twice as fast, the air holds you back 4 times as much, and you need 8 times more power to keep going that speed. Our designers and engineers across all disciplines worked hand in hand with our own team of ex-Formula One aerodynamicists to make the truck not only look great, but perform even better. Together, we obsessed over our bounty targets. Just like in racing, where everyone is united in shaving milliseconds off lap times, the bounties keep us focused on chasing physics. When we finally achieved our target, we reset it to continue challenging ourselves and go even further. One small improvement, let's say a millimeter change in the roof height, equates to a $1.30 savings of battery cost. And as a result, the aerodynamic efficiency of our truck is more than 15% better than any other pickup truck on the market today, and will ultimately result in longer range and lower costs for our customers. If we go underneath the vehicle, you can see how we streamlined the underbody to manage the air. Starting at the front, we made the bolt holes shallower and carefully directed air around the tire and suspension. We also painstakingly designed underneath the car to steer the front tire wakes directly onto the rear tires, hiding them from the high-speed flow and ultimately reducing drag. Changes like this can contribute to an estimated 4.5 more miles of range for the customer. Moving to the back of the car, we position the drive units as low as possible to reduce the angle of the half shafts, making them last longer and minimizing wasted energy caused by friction in the joints. We then sculpted the motor case to allow the air we carefully managed at the front pass under the vehicle uninterrupted to reduce the size of the wake. Here, the roof was sculpted to carefully shed the high-speed air on top in a teardrop shape over the bed, creating a virtual surface for the air to completely skip over it. To the air, it's no longer a truck. We also applied the same mindset to the side mirrors. Instead of separate motors for glass adjustment and another motor for folding, we've merged those functions into a single actuator. The entire body of the mirror now moves. The mirror body size is now more than 20% smaller than a conventional mirror, which reduces mass, saves on costs, and unlocks a more aerodynamic shape, resulting in 1.5 miles more range for the vehicle. We also needed to reduce mechanical friction. So the team obsessed over every single bearing, seal, and joint inside the vehicle. We treated the drive unit oil management system just like a race car. Our control software, which can be updated and improved over the air, adjusts the speed of the electric oil pump so it runs at the lowest speed possible to cool the motors and lubricate the gears, while carefully designed jets and baffles reduce windage inside the gear case. And to make sure we aren't letting any energy go to waste, we enhanced the design of our regenerative brake system, which, like all electric vehicles, captures the kinetic energy, converting it into usable electric power for the high voltage battery. Our new design will save us around $100 in battery cost. The result of all this work? If the same battery was married to the aerodynamics of the most aerodynamically efficient mid-sized gas truck in the US, we believe our new electric truck would have nearly 50 miles or 15% more driving range and a 30% improvement at highway speeds. That's what happens when every curve, every surface, every detail has been obsessed over and over again, and works together as a system. Now let me turn it over to Vlad to talk about the vehicle structure.
Weight is another one of our greatest efficiency robbers. Our engineering team had a philosophy: best part is no part. If the part is necessary, then it must serve multiple purposes. It's not easy to find those opportunities. That is why we need the close collaboration of a small, nimble team. So first, we focus on reducing one of our biggest contributors to the vehicle weight, body structure.
To do this, Ford is using large aluminum unicastings for the first time.
These unicastings make the structure significantly lighter, delivering more than 27% advantage in casting weight over our competitors. They also serve as a structural element of the mixed metal body structure architecture, which is the backbone for both vehicle and assembly process. To put a final point on it, by comparison to the Maverick, has 146 structural parts in the front and the rear structure. The mid-size electric pickup truck will have 2 parts. Using unicastings enables 25% fewer fasteners than typical program. With reduction in parts comes reduction in joints, sealing, therefore robots in the factory, giving us immeasurable gains in product quality and the throughput. Let me hand it over to Alan to talk about the battery.
Now let's take a look at another big contributor to weight, the battery. Our holistic focus led the team to select a low-cost chemistry called lithium iron phosphate, or LFP. With no nickel or cobalt, our battery cell contains lower-cost ingredients over other battery chemistries. Next, we focused on the packing of the battery cells. Think of it like a puzzle. We're trying to fit the most battery material possible inside the pack. Our prismatic LFP form factor enables an incredibly efficient cell-to-structure architecture. This architecture essentially turns the battery into an integral part of the truck's skeleton. The battery pack also uses a multi-layer, single-piece, flexible circuit board. This board integrates low voltage, high voltage, and thermal sensing connections, reducing hundreds of bus bars and wires into a single part. We can measure voltage and temperature and connect each cell using this hyper-efficient module. Overall, the cell-to-structure architecture reduces non-cell cost. It also works together with a super compact, in-house designed power electronics inside the battery pack. This eliminates extra connectors, enclosures, mass, and overall volume. Instead of carrying the cells, this new architecture couples the cells directly to the structure. This makes the cabin quieter and the structure more capable of excellent dynamic performance. It's also a key enabler in delivering our new universal production system, which means our family of electric vehicles will be super fun to drive, a non-negotiable here at Ford. And let's not forget, we're using proven, long-lasting battery cell technology that ships in millions of vehicles today. We then married this battery technology with Ford's new innovative approach to make these cells into a pack. We'll be making the battery cells right here in the United States at Blue Oval Battery Park in Marshall, Michigan. Now let me turn it over to Lucas to share more about our electric vehicle architecture.
Okay, this is where we get a little more technical, but stay with me here. Vlad already told you about our philosophy, and you see it come to life in our approach to the vehicle's electrical architecture too. I joined the team 2 years ago when Ford acquired Automotive Power. At AMP, we specialize in pushing the limits of energy management, and we've brought that expertise here to optimize hardware and software for faster charging and smarter battery performance. With this platform, we're moving to a zonal architecture, where we're integrating multiple vehicle functions into a small number of modules. Conventional vehicles are built with over 30 scattered electronic control units, or ECUs, which are the brains of the vehicle. In the past, they were individually housed and sourced from various suppliers. This results in a tangled web of connectors and wiring, adding complexity and weight and cost to both manufacturing and assembly. Our platform combined those into 5 main modules, drastically reducing cost and complexity of the wire harness. We're also moving from a 12-volt system to a 48-volt system, which allows us to reduce the copper thickness of the harness. In fact, these changes helped us make the mid-size electric truck's wire harness 4,000 feet shorter and 22 pounds lighter than one of our first-gen electric vehicles. We did not stop this consolidation effort on the zonal modules, but carried the same philosophy to the power electronic components, which are the muscles of an electric vehicle. For example, the DC to DC converter, which converts the 400 volts battery power to 48 volts, now shares a board and components with the AC to DC charger. This single module also manages power distribution, battery management, and provides AC power back to your home during an outage. Grouping these together allowed us to consolidate common parts such as sensors and auxiliary supplies, reducing the number of components and printed circuit boards. This results in a surprisingly small and serviceable unit. Despite all its capabilities, it's elegant in its simplicity, and we call it the e-box. Lastly, I want to talk a bit about some of the diagnostics we intend to run on the battery packs. We're leveraging machine learning to create a predictive model for the battery pack, which will track and adapt its usage based on both historical data and real-world conditions. This will, for example, allow us to adjust charging rates to help prevent degradation of the battery over time. Let me turn it back to Alan.
So that's how the team is collaborating to develop the platform. We're using a true systems engineering approach across design, product development, software engineering, supply chain, and manufacturing to completely rethink vehicle production. Every decision centers on how much we can reduce the size of the battery. How can we give more to the customer so they get better value? For our industry to truly unlock the transformative potential of electric vehicles, the strategic integration is foundational to achieve cost parity with gas vehicles. Gas cars have been optimized over the last 100 years, but there are still countless ideas for reducing the cost and increasing the capabilities of electric vehicles. The technology, engineering, creativity, and innovation are already happening. We need to scale these advancements and deliver them to driveways across America and around the world. We can't wait to share more as we continue on our path to deliver our universal EV platform and a family of compelling and fun to drive affordable electric vehicles. Thanks for coming along for the ride. We can't wait to get you behind the wheel.